All right, here's a 2D kinematics problem. This one's a little bit tricky because we've got a wall here that this projectile is being shot at, and we don't know exactly where on the wall the object is going to land. As I've drawn this trajectory here, and usually we draw trajectories with a dashed line, I've drawn it as though it's going to land beneath where it is, but you can envision a situation where this is, thrown so fast that it lands somewhere up here instead, actually above where it's being shot from. So we don't know exactly yet, but this is just sort of some sense of what's going on. There's a ball being shot from one roof to another building. And so, of course, first, no matter what the question is that they're asking, we need to write out all the givens. There's no question about that. So when you write out the givens, the first thing you want to do, oftentimes for these projectile motion questions, they give you some information about the hypotenuse, basically the magnitude of this vector. And in this case, they told us that this vector is 20 meters per second and it's 40 degrees above the horizontal. So straight off the bat, we should be able to break this into its components, into its x and y components. So let's go ahead and do that here. So the x component of my vector, make sure that your x component of the vector comes straight down from the tip of this vector, just like that. It doesn't go any further or smaller. So this is going to be our v naught x, and then right here, this will be our v naught y, just like that. And straight off the bat, we can find what v naught x and v naught y are. In fact, maybe I'll do that right over here to save us some space on the other side. So v naught x is going to be v naught times cosine of 40 degrees in this case, and what I end up getting for this is 15.32 meters per second. And then we can do the same thing for the y-axis. So v naught y is going to be v naught sine of 40 degrees, and when I plug that in, I get 12.86 meters per second. I'm playing a little fast and loose right now with my sig figs, because I'd rather hold on to too many sig figs and then sort it out at the end than over approximate. So here we are, so we've got v naught x and v naught y. We should also write out the other givens. So let's do that here, and I want to make sure for two-dimensional kinematics questions that you keep your x and y components separate. So let me start with the position. So I'll call the position 0, which means that I should probably indicate somewhere here what my coordinate system looks like. Oftentimes it's convenient to say that the ball or the projectile that you're throwing starts at the origin, and so that's what I'm going to do here. So I'm putting the x and the y-axis through this so that this is actually starting at the origin, which means that my x naught is 0 and my y naught is 0. We don't know how high this building is, right? So I don't see any other better choice here. V naught x, we just said, was 15.32 meters per second. V naught y, we just said, was 12.86 meters per second. And then because there's no wind, right, so we've covered position, velocity, now let's talk about acceleration. Because there's no wind or anything to sort of force our projectile forward or backward in the horizontal direction, our acceleration horizontally is 0. But always, when we're dealing with free fall, at least near the surface of the Earth, our AY is going to be negative g, where g is some number. In this case, our number is negative 9.80 meters per second squared. Okay, perfect. So now we've written out all of our givens and we've kept everything separate here. Part B, whether it's explicitly written or not, is often finding the time, finding some end time, whether it be the time where the ball reaches its peak, or in our case, we're probably going to be interested in when it hits the wall over here. So part B, find the time it takes to get to the opposite side. So in other words, we're going to talk about this full time. If you're interested in the time to the peak, what you can do is you can think about the final velocity there vertically as being 0, because right at the peak of motion, right at the peak of a trajectory, the vertical velocity component is 0. So here we are. Find the time that it takes to get to the opposite side. So in this case, the only information that I know about the opposite side, I don't know the final velocity, right? It's unlikely to be the same as what it is over here because this is probably not a mirror image. And so the only thing I know is that they've told us that the second building is 50 meters away. In other words, they've told us that if this is x equals 0, that this over here is x equals 50. So this is sort of like our final position. So in fact, I'm going to add that. If you don't mind, I'm going to squeeze it in right here, 50 meters right there. Okay, so we're looking for a time. We've only got a few kinematics equations to deal with, and in fact, they're identical for the x and y components. The only difference is literally the subscript here. So I'm just going to write out sort of the two main ones that we end up using very often. This one is very powerful, t plus 1/2 ax t squared. The other one is not involving the times. It's only involving the velocities and the displacements, something like that. And again, we could write out the exact same equations where I replace all of the x's with y's here. Now in this particular case, the only information that I really have is about the x. So that's what I'm going to have to use. I'm going to have to use x as opposed to y here. I think, that seems to make the most sense to me. I've got everything but the t for this one, so I think this is the one that I'm going to start with. So xf is equal to x naught plus v naught xt plus 1/2 ax t squared. What's really nice is that, at least in this case, since we're dealing with the x component, the acceleration term drops out, and our x naught is also 0, just because that's where we've defined the origin to be. It's right there. And so now we're just solving for t. So I'm going to divide by v naught x on both sides. So I'm left with something like this, and my time ends up being about 3.26 seconds. Okay, so this is the time to the other side. Now, the next question is going to ask about where does it land vertically? Does it land above or below, and by how much? Above or below where we started, and by how much? So this is kind of the part C to this question. I'm going to trust that you've already written down the given so I can erase it here. All right, so part C, basically where vertically does it land? How far above or below? Is specifically what the question is asking for. All right, so in this case, we're obviously looking for some sort of height information. So we're going to have to use the y component of one of these equations. We've got the, we don't know anything about VFY, and we also don't know YF, so that's going to be trouble. But this one could potentially work, because the only thing that we don't know is YF. Right? And again, I'm thinking about these as the y versions of these equations as opposed to the x. So let me write the y version of that top equation. YF is equal to y naught plus v naught yt plus 1/2 ayt t squared. We've got everything now, including the time, except for YF, and that's the thing we've already solved for, which is nice. Again, we've kind of taken our origin to be right where it started, so that's 0. Our V naught Y we already determined, that's 12.86 meters per second times this 3.26 seconds plus 1/2 times negative 9.8 meters per second squared times t, 3.26 seconds squared. And so I end up with negative 10.15 meters. So what's this mean? This means that we land at negative 0.15 meters on my axis. So looking over here we go. So this is 0 on the y-axis, right? Again, this is my y-axis and this is my x-axis. So on my y-axis, I'm landing below where we started. In fact, I'm landing 10 meters below where we started. So wherever this lands right here, this is 10.15 meters.